So we're going to look at an overview of this graphical analysis so far, everything we've done so far, and what the general shapes are that we should be looking for. If you were ever going to put a star or a sticky note or something on the page, I would put it on this page because it's going to be really important to make sure you know what certain lines mean, like what a curved line on the distance time graph means, what a straight line means, all that kind of stuff. And this is a really good page to make or to reference. Okay, so I've kind of got them written here. Stationary object on a distance uh, or a position time graph is going to look like a straight line, right? It's going to be a straight line. It's going to either be in the positive or the negative. It just means that they're standing to the, I don't know, to the right of your reference point or standing to the left of your reference point, but they are standing if it's straight. Okay. Um, this one, if you've got a straight line going up or a straight line going down, going up is going to be a positive velocity, going down is going to be a negative velocity. A curved line on a distance time graph is going to be acceleration. And really, the only time you're going to have a curved line is when it's accelerating. And that's the only one, right? If you look through all these, the only time you have a curved line is on a position time graph, and it means it's accelerating. Positive acceleration would be going in this direction. Negative acceleration would be going that direction. An easy way I remember that too is if you think about it, if I have a happy face, you can see that the mouth on the happy face, that's positive, right? So he's positive, so he's going up. Negative acceleration would be a frowny face, means you're going down. So this kind of like, this one looks kind of like a frowny face. Is the one half of a frowny face. And we'll see actually as we do acceleration, this graph could go like that too, and that would also be negative acceleration. So I find it a little like a helpful thing to help me remember. So okay, now moving on to velocity time graphs. A straight line on a velocity time graph means constant positive velocity on the top, constant negative velocity on the bottom. Remember what positive and negative mean? They just mean which direction you're going. So positive would be to the right or to the east or up. Okay, you have a slope or like a on a velocity time graph. It's going to be positive if it's going up. It's going to be negative if it's going down. And this one's kind of intuitive, right? Because we're starting from a velocity of 0. So this would just be like, if you started here, this line would be somebody speeding up eventually, right? Like you taking off in your car. This line would be you slowing down at a red light. Okay, this one though is a little bit less intuitive. We've still got a negative acceleration, but in this situation, we start with some velocity, right? This thing had like some velocity to begin with. This is like a ramp. So that ramp question that we did, a ball rolls up a ramp. It comes to a stop at that point. That's right here. That's where it comes to a stop, is right when the velocity would be 0. Whoa, that was weird. Sorry about that. Let's go zoom in. Okay. Okay, so it comes to a stop, right? The top of our ramp, right? And then rolls back down again. So its velocity is going to be in the negative direction on the bottom half of the graph after that. But the slope is the same in the entire time. So this ball's journey going up and then going back down, its acceleration was the same the whole time. All right, we'll talk more about that though. Okay, and then acceleration time. These ones are pretty easy actually. Acceleration, if it's a straight line on the above, it's going to be a positive acceleration. If it's a line below, it's going to be a negative acceleration. And positive acceleration doesn't mean speeding up, and negative acceleration doesn't mean slowing down. It can mean that, but we're going to talk more about that before. But you can look at our ramp situation and know that's not true, because this thing had a negative acceleration the entire time down the ramp, and it was slowing down and then speeding up like it did. Yeah, so that idea that constant acceleration means always speeding up and negative acceleration means slowing down, that just doesn't add up. All right, so let's do these practice problems. I'd like you guys to go ahead in a minute here and just pause the video, and then I'm going to just show the answers like I did before. So you can go ahead and pause the video now. Okay, so let's just go through these first ones. So you can see that I had a velocity time graph so the slope is negative, right? It's going down. So I know that acceleration is going to be negative. And the acceleration graph is always a straight line, right? That's the only one we ever do with an acceleration time graph. And it's going to be on the bottom half of the graph because it's going to be a negative acceleration and a straight line. Okay. Number 2, we had a positive slope on the distance time graph. Positive slope on the distance time graph means a positive velocity. So it's going to be a positive straight line on the velocity time graph. And then that's that, like, dotted line going straight down, or just that straight line going down. And then at this point, it stops moving, right? So its velocity is 0. So the velocity carries on at 0. All right, this next one, I've got velocity to acceleration. The velocity, I have a positive velocity going up, right, the whole time. So the slope is positive. That slope is the acceleration. So I just have a straight line going across there until this point. And then at that point, my velocity is equal to 0. Or sorry, my velocity stays constant, not equal to 0. My velocity stays at, this could be like negative, or this could be like 4 meters per second. So if you have a constant velocity, that means you are not accelerating. There's no acceleration, so the acceleration stays at 0. If you haven't paused the video and done this one already, then go ahead and pause the video now, and then I'll pop the answers up again. Okay, there wasn't actually too much to write for this one. So what is the instantaneous velocity at 5 seconds? So all you do at 5 seconds is just, drill or figure out where that point was. I made a line tangent to that. And then you just find the rise and the run. You'd figure out what that is. And you should get approximately negative 2.4 if you do that, right? And know that your rise should be a negative number because it's going down. And maybe you've never seen this symbol before. That just means approximately. So your answer might be 2.2 or 2.3, something like that. Okay, B, how far did the object travel from its origin after 6 seconds? So after 6 seconds, so just that's that red dot I've got here, it started at 23. It went down to 14.5. So I just went 14.5 meters minus 23. That I just did, like, the final minus the initial, and that gave me negative 8.5 meters. Okay, is the acceleration positive or negative? Well, this thing kind of looks like a frowny face, I'd say, right? It's like the half of a frowny face, so it's negative because it's a negative person. But the other way of thinking about it, the more scientific way of thinking about it, is that your acceleration is going to get more and more negative as you go down. So if I look at like this point here, and I drew another instantaneous velocity, from there to there, it's going to be even more negative. Like this was negative 2.4. This one here, maybe that was like negative, 8.6. And it's going to get more and more negative as you go down. So the acceleration is negative. But like I said, we're going to talk a bit more about that in an upcoming lesson too. So for this last one, I'll just kind of go through with you. I'll write down the answers in real time. So it says, with this velocity time graph, what is the instantaneous velocity at 8 seconds? Really, all you got to do here is just look up to that point and look and see what the velocity is. That's the instantaneous velocity at that point. So it's going to be 10 meters per second. What is the acceleration from 8 seconds to 14 seconds? So this could just as easily say, what's the slope from 8 seconds to 14 seconds? Because acceleration on the velocity time graph, that is the slope. So if you do that, I've got change in velocity over change in time. Could just as easily say rise over run. You end up with negative 2.5 meters per second squared. What is the displacement from 8 seconds to 16 seconds? So displacement on the velocity time graph, maybe you've forgotten, is the area under the graph. When I say under the graph too, people think like just all under the graph, but it's the area that's trapped between the curve and the line. So it's this, and it's this. And I need to take, maybe I should have made the line there too. And I need to take the red one here and subtract the green one. We got to figure out what like the net result is. So if we do that, we just got to figure out the area of the first one is going to be called D1. And that's going to be 1/2, because it's a triangle, times, what's that at, 10? Yeah, 10 meters, or 10 meters per second. And then times the time of 4 seconds. So this is going to be, oh, I forgot seconds. This is going to be 20 meters. And positive 20 meters because it's above the line there too, right? So positive 20 meters. Okay, and then the second one, we're going to have to split this up into two because we've got a triangle and a square there. So let's do the triangle first. So D2 is going to be, looks like -5. Well, 1/2 too because it's a triangle. And then -5 meters per second times, that was only for 2 seconds. So that's going to be -5 meters. Okay, second one. And then we just got to do that square, that last part there. So that's going to be not 1/2. Call that D3. It won't be 1/2 because it's a square. So it's just going to be -5 times, and that was also 2 seconds. Oh, meters per second and 2 seconds. So that's going to be equal to -10. So then our displacement, and technically I should have been doing triangles and little arrows over top of all these, but you'll notice that quite a few people just get kind of lazy because they're tired of doing it. But there they are. So my total displacement there is going to be equal to 20 meters plus -5 meters plus -10 meters. So my displacement here is going to be equal to +5 meters. So that's it for the practice problems. I'd like you guys to go ahead and do the hand-in assignment now.